Hello, my name is Daniel Huterer Prats. I'm a second year PhD student, and today I'm talking about reinforcement learning for space-to-space surveillance, in particular autonomous scheduling for resident space object imaging. This was a project in combination with interactive aptitude as part of an STTR. First, let's jump into the motivation. Clear need for space-to-space surveillance, and this need is increasing as there's a growing number of RSOs in orbit around Earth. There's over tens of thousands of expected satellites to be launched in the next coming decade, and the number of sensors to track these objects is not following that same trend. Traditionally, many ground-based systems were used in order to keep track of these RSO catalogs, but these come with limitations. They have limitations in terms of weather, atmospheric disturbances, night-only observations for some of them, and as well as fixed fields of regards. In contrast, if we look at space-based sensors, they avoid these atmospheric disturbances and weather effects mostly, and over a course of a whole orbit give you an effective global field of regard. And so there is a need of space-based sensors to aid with this growing SDA challenge. Now, jumping into how challenging it is actually to create an RSO imaging schedule, if we look at agile Earth observing satellites, there you're keeping catalog of a number of ground targets, and you have to decide on the best sequence to image those. Here, all the targets are stationary or slow moving, and that sequence is quite predictable, as all the targets that you're going to image are kind of on your ground track below you, and you need to do smaller maneuvers. If we now want to convert this into an RSO imaging schedule, we want to keep a catalog of space targets. Here it is much more challenging because they're faster moving as well as slow moving targets depending on the relative orbits. The sequence of targets is much harder to predict in terms of which ones you should actually be pointing to, and they can come from all types of directions, from behind you, from above you, from the sides, etc. So you might have to actually do attitude maneuvers that cover 180 degrees, and you have to be quite agile with that. The problem statement, the way that it was set up in this paper here, is a LEO to LEO imaging satellite where you have one scanning satellite and 100 targets. They're all in LEO in randomized orbits, and you have eight orbits in order to image all of them, which equivalates to about 150 imaging actions. The objective is to maximize the fraction of successfully imaged targets out of all the RSOs in the environment. The total action space looks as follows. You have imaging actions, you have charging and desat, as well as downlink actions. So those three are in terms of keeping the spacecraft safety constraints in check. And the ground stations are there. There's around 7 in the simulation, which are there to serve as the downlink opportunities for the scanning agent. The main constraint is target visibility constraints, meaning that we care about do we have current line of sight with the target that we're trying to image, what is its illumination factor, and is it sufficiently illuminated for us to actually be seeing it. And as I mentioned before, there's also spacecraft safety constraints in terms of battery levels and reaction wheel limits. And we're also considering a restricted storage capacity such that the agent is forced to downlink every once in a while in order to free up its buffer to do new images. The overall architecture of the simulation can be seen here, and it's also in the paper. And we are really fully simulating this scanning satellite as well as 100 targets in our simulation. Here we're doing this simulation in Basilisk, which is a fast and flexible spacecraft simulation framework, and then we're using Gymnasium as our RL interface, and together we're basically combining this as a wrapper with BSK RL. Our Markov decision process formulation is as follows. The first 3 elements are about the spacecraft health and in terms of the data storage, the battery percentage that it's at, and the reaction wheel momentum of the 3 reaction wheels that it is using. The next observations are for 10 targets within its line of sight, and it includes the elevation angle, the current pointing error, the distance the distance to the target, as well as the relative position to the target in the scanning agent's hill frame. Also, we're giving it information on when it is entering and leaving eclipse, as well as when it is entering and leaving ground station windows. The reward function is very simple, where you get a reward correlated to the weight or the priority of the target that you're imaging, subject to illumination constraints, meaning that the illumination of the target has to be higher than the threshold, line of sight at the time that you actually aligned with the, or that you're pointing to the target, and lastly also pointing error constraint, where you need to be within 0.01 modified Rodriguez parameters of angular error, in such that you consider it a successful image. In terms of the transition function, here we're looking at a deterministic transition, which is from our high fidelity simulator Basilisk. The step duration delta t varies in between the actions, so imaging action has 300 seconds, but charging, DSAT, and downlink may have varying durations as well. And we terminate the episode whenever the satellite runs out of battery, or if the reaction wheels are too fast. Now, to get a baseline comparison, here we're looking at unlimited resources, so without having the need to charge or downlink or DSAT, because we have unlimited battery, unlimited storage, etc. To give a fair comparison, we're comparing it to a heuristic policy, which uses the full list of targets that are currently within line of sight, so it might be greater than 10 as well. And from those, it chooses the one with the closest angular pointing error, and that is a behavior that was observed by another paper that did space-based scheduling. Here, the heuristic policy is fully reliant on the shield in order to do spacecraft resource management, which we will see later. But this baseline comparison is now isolating the imaging problem. So we're not looking at charging or DSAT or downlink actions at the moment. And the full performance here is dominated by line of sight geometry and how you select the targets. We see here that the reinforcement learning policy does perform one target on average better than the heuristic policy, but it is also doing that in a clever way. And here, the optimal value is not exactly 100. It depends on exactly the simulation and the seed that you're getting, because you're randomizing all the orbital elements, and therefore sometimes you cannot even image all the targets, especially considering eclipse constraints as well. But the reinforcement learning policy is clearly trying to choose targets that are illuminated. So we see here a clear difference between 89% to 71% of choosing illuminated targets at the decision points. So this is basically implemented as imaging behind if you're about to enter an eclipse, and imaging in front if you're about to leave an eclipse, since the targets over there will already be lit. Now, let's look at the performance comparison under these restricted resources. So here we do have a shield intervention for the heuristic policy that kicks in whenever you have a full storage, or whenever your battery level is below some critical level, which was here set to 20%. And if we look at this particular seed, we see that the heuristic policy drops below critical levels at the beginning, and it just happens that the batteries, it starts getting very low as it is entering eclipse, which is when it can barely, which is when it cannot really use charging action even to increase the battery levels. Then it also waits and collects images until it has a full storage, and then keeps downlinking and even loses daylight time in order to try to downlink until it reaches a ground station window. So the value of the data is lesser because you're downlinking older data. If we look at the reinforcement learning policy, here we see an interesting behavior where we are selecting targets. We are downlinking when we are in eclipse. So there's a clear kind of eclipse-driven downlink strategy, which is also interesting because during eclipse, most of your targets in line of sight, if you're in Leo, are also eclipsed. Therefore, this is a good time to be downlinking, and you get a much more frequent downlink frequency. And as we can see here, all the images that are being downlinked, they're younger, therefore more valuable to operators on the ground. Also, it did not require any charging actions or DSAT actions for this exact same seed that we looked at compared to the previous case in the heuristic policy. Here we are choosing targets that at the same time also allow it to charge, which is pretty valuable. This becomes harder as you have less targets to image. This is not as doable anymore later down in the episode. Then, this is from a future paper that is not yet in the one presented here. Here we're also looking at increased training durations with larger batch sizes. And what the goal here is to teach the reinforcement learning policy to only downlink during ground station windows, to really optimize for that. Here we see that it does learn that behavior, and it really only triggers downlink actions when it's around ground station windows. And this gives you very good performance, better than the reinforcement learning policy we just saw before, and better than the heuristic policy that I showed at the beginning. So here we have the largest number of image targets, as well as the largest number of useful downlinks, which are when an imaged target is also when an illuminated image is also downlinked successfully. And here we also see near optimal performance in terms of the downlinks, because it is trying to use almost all of the downlink windows. In conclusion, we see that reinforcement policies can handle the dynamics of LEO to LEO imaging, despite having sometimes very large, very fast relative motion. And it is also doing that under stricter resource constraints on the spacecraft. So overall, space-based sensor tasking using reinforcement learning is a promising approach to help manage the growing SDA challenge as the number of objects in space is growing larger and larger. Here on the right, we see a simulation of that seed that I was just showing. Future work will include analyzing the trade-off between how we reward imaging versus downlinking, and finding a balance of depending on how the client or the user would like to have it, and expanding the RSO catalog to various orbits, so having MEO, GEO, and LEO perhaps also in the same catalog, etc. And we would want to increase the ability to also re-image targets, so that we can really maintain, in terms of uncertainties, a specific set of RSOs that we want to look at. Also, later we want to expand this to multi-agent reinforcement learning and have a collaboration between various scanning satellites in order to maintain a RSO catalog, and do that without having fixed imaging time durations, but really only slew as much as you need and then switch to the next target. Thank you very much.